Hello everyone, welcome to the 17th lecture of the second module on analog meters, and we are discussing the course on measurement and instrumentation, and we are in the fifth week of this course. In the previous class we started new kind of instrument which is electrothermic instrument, and we talked about hot wire instruments. Along with hot wire, we also saw that there is one more kind of electrothermic instrument, that is thermocouple kind of instrument. Although thermocouple itself is a part of our third module where we will talk about transducers, means the thermocouple itself is a kind of transducer, but it's very important to discuss about the thermocouple instrument, and that's why what I will do is I will just give you overview of what is thermocouple, okay, and on what principle it works, okay, and then we will see that with the help of a PMMC tool how this thermocouple instrument can be used to measure, say, certain electrical parameter, for example current, okay. So let's first see what is basically a thermocouple, and then we will try to understand the thermocouple instrument itself, okay. To understand the thermocouple, we have to recall a concept of work function, okay. So now consider that when there are two different metals, okay, having different work functions are joined together, something like this, okay, a voltage is generated at the junction. So say if you have material A or metal A and then metal B, okay, these two different metals, okay, are joined, okay, a voltage is generated at the junction which is proportional to the temperature, okay, or you say temperature difference, okay. We'll see this in detail, okay, and this junction based device is known as a thermocouple, okay. So this principle is used to basically convert heat energy to electrical energy at the junction of these two conductors, okay. So this is a basic idea of a thermocouple instrument. Of course we will talk about this in detail, but you can see that there is a heater through which a current is flowing, and along this thermocouple you have attached a PMMC meter. If you remember, the PMMC tool were used primarily for the measurement of DC values, okay. So the principle of operation, as I have just mentioned, that it's very simple. So when two dissimilar metals form a closed circuit, okay, and their junctions are maintained at two different temperatures, a thermoelectric EMF is generated, okay. So basically you can say that these thermocouples are also can be called as a thermoelectric device, okay, or can be classified under thermoelectric device, okay. Now this EMF is a function of the temperature difference between these two junctions and is basically used to measure the temperature as shown over in this figure, okay. So the thermocouple instruments works on the principle of Seebeck effect, okay. So we will discuss about this Seebeck effect in more detail when we will talk about the transducer, but in this lecture I will just give you an overview that what is this and how this Seebeck effect helps. But with this metal kind of junction there are some other effects also, like Peltier effect and others, that we will see in more detail when we will talk about this thermocouple based devices in our transducer module, okay. So now let's try to understand this Seebeck effect in little detail, okay. Now consider that two different metal wires, say metal A and metal B, are joined to form two different junctions as shown over here in this figure, okay. So this is wire A and this is wire B, okay. Now the hot junction, I am calling this a hot junction, and say it is at temperature T1, okay, and this is the cold junction. I am also calling this reference junction, and this hot junction I am calling as measuring junction, okay. So two different junctions are there. One is at elevated temperature, which is the hot junction, which is also known as the measuring junction, and then there is another junction which is known as reference junction, and it is at lower temperature T2, okay, and we also call it cold junction, okay. Now since these are two different materials and these are at these junctions are at two different temperatures, okay, so when these temperatures are not equal, okay, there will be certain kind of EMF which is produced in this closed circuit, okay. Now this magnitude of the EMF that is generated in this kind of arrangement is dependent on what kind of metals we have used, this metal A and this metal B, and their temperature difference between T1 and T2, or say T1 minus T2, okay. So the magnitude of the EMF which is generated is dependent on the type of metals used, metal A and metal B, and their temperature difference of their junctions, okay. Now let's see the working of this thermocouple kind of instrument, okay. So this was the basis of the Seebeck effect, and exactly this thermocouple instrument is based on the Seebeck effect. So again you have to call these two metal wires and get connected to form the measuring junction and to form the reference junction, okay. The heat at the junction is produced by the electric current flowing in the heater element, okay. The heater element is basically giving you the measuring junction, okay. The hot junction is placed at the point where the temperature is to be measured, okay, and the cold junction is kept at a known temperature, okay. Due to the temperature difference, the electrons diffuses differently in the two metals, okay, and this create a small EMF. When I say small, it is actually very small, in the range of say microvolt to maximum to a few millivolt, okay, in this circuit, okay. The EMF at its output terminal can be measured with the help of a PMMC kind of instrument, okay. But this PMMC instrument is not exactly what we have used earlier. We will see, if the time permits, that there are certain modifications done in this PMMC instrument to be used in the thermocouple kind of instrument. Particularly the air gap has to be tuned, okay, for being suitable for the thermocouple based, or to be coupled with the thermocouple based instruments, okay. The EMF produced is basically proportional to the temperature, as we have seen in the Seebeck effect, and hence to the RMS value of the current. If you remember, in the PMMC tool, we have not talked about any RMS values, because there we were mostly dealing with the DC current or say DC voltage, okay. In this case, in the thermocouple instruments, the scale of the PMMC instrument can be calibrated to read current passing through the heater, okay. And that is what the ultimate aim is. We are able to measure, if say the heating value or the temperature value, we can of course talk about, or we can comment about the current that is flowing through the hot junction, okay. So the idea here is that in such a way that it can be used to measure both AC and DC signals, okay. But in the case of PMMC, if you remember, we have seen that it can only be used for the measurement of DC values, okay. So please note here that when you are using this PMMC instrument in conjugation with this thermocouple or thermoelectric arrangement, okay, it can be used to measure both kind of signals, which is AC and DC. In fact, at even higher frequencies, the performance of thermocouple instruments are very good, okay. We have seen in general that the electrothermic instruments behave very nicely when, even if you are using it at elevated temperature, and that was the basically edge of using this electrothermic instrument over the other kind of instrument, say moving iron kind of instrument, okay. So the most attractive feature of thermocouple instrument is that they can be used to measure current and voltage at very high frequencies, as I have just mentioned, okay. So these instruments are very accurate on frequencies which is even higher than the 50 megahertz frequencies, okay. Now let us try to understand in little detail that how basically they work, okay, and how to calculate the deflection, okay. So the thermal EMF developed in a circuit which is composed of two different metals with junctions kept at two different temperatures, say T1 and T2, okay, may be approximately written as E equal to A T1 minus T2 plus B T1 minus T2 square, and even it can go further like T1 minus T2 cube. Please note that here it has to be T1. Okay, so T1 is greater than T2. We have already seen this, that T1 is what the hot junction is at, and T2 is the reference junction, which is the cold junction. Okay, so this has a different terminology, like A T1 minus T2 plus B T1 minus T2 square plus C T1 minus T3 cube and so on. But the value of B, C and all is so much diminished that even we are taking to this two terms. So one thing that you can understand from this equation, that the EMF generated is highly nonlinear in nature. Okay, and this A and B are the constants whose value depend on the kind of metal it is used. Okay, and that's why we will see in the transducer section that in the transducer module that although if you connect any kind of metal metal A can be any metal, like anything. Okay, and metal B can be anything, but you will have a certain kind of EMF generated. But then there are certain standardization done to this thermocouple by the industry, and there are altogether 6 or 7 different kind of thermocouple which is available, and which are of different fixed metals, like metal A is this, metal B is this. Okay, so these things are fixed, and we call it certain type of thermocouple, like K type and so on. Okay, we'll discuss all these things in the next module, but what right now we are discussing is we are trying to correlate this thermocouple measurement with the analog instrument. Okay, so as I have mentioned that E is equal to A T1 minus T2 plus B T1 minus T2 square. Okay, and A and B are constants whose values depend on the kind of metal it is using. Okay, so let del theta is the temperature difference of hot and cold junction, of course in degree Celsius. So basically what I am trying to say is, say delta theta is equal to T1 minus T2. The EMF value can be written as A del theta plus B del theta square. Okay, so I am calling this say equation 1. Okay, this equation I am calling as equation 1, and I am calling this equation say equation 2. All right. So thus EMF of a thermocouple is approximately a parabolic function of the temperature difference between the junctions, or the del theta value. All right. So the approximate values of constants A and B as per different textbooks are, like A is like 40 to 50 microvolt or little bit more per degree Celsius difference of temperature, and B, the value of B is very less. It's say few tenth or hundredth of a microvolt per degree Celsius square. Okay, so if you see the value of B is very small if you talk in terms of the values. Okay, and A is very large as compared to the B value. Okay, so if a temperature difference of say 100 degrees Celsius exists between the junctions, an EMF of approximately say 5 or 5 to 10 millivolt will be available, and not more than that. Okay, means that even if you have large difference, which is say like 100 degrees Celsius, which is really a large difference when you talk about the difference between hot junction and, or the say measuring junction and the reference junction, then also the EMF value is not very high. It's 5 volt to say 5 millivolt to 10 millivolt. Okay, and that's why the sensitivity also of these devices are not very high. Okay, so in some instruments the hot junctions have very high temperatures, and EMF value of the order of say 12 millivolt or 15 millivolt can be produced, but not more than that. Okay, now the current flowing through the heater element produces a heat which is proportional to I square R, that we have already seen. Okay, where I is the RMS value of the heater current and R is the resistance of that particular heater. Okay, the temperature rise over the ambient or over the room temperature of the hot junction is basically directly proportional to the heat produced, or say is directly proportional to I square R. Okay, so the rise in temperature of the hot junction is directly proportional to the current, or the square of the current flowing through it, or say rise in temperature of hot junction is directly proportional to I square R. Okay, Now, if the cold junction is maintained at ambient temperature, which is known to the user, okay, the rise in temperature of hot junction is equal to difference in temperature between the hot and cold junction, or hot to the ambience temperature. Okay, hence the difference in the temperature delta theta is equal to rise in the temperature, or delta theta is directly proportional to I square R, or if I put a constant, I can say that delta theta is equal to K1 I square R. I am calling this equation 3. Okay. So, delta theta now is an established fact that is equal to K1 into I square R. Okay. Now, the difference in temperature between hot and cold junction produces a EMF, which we have already seen from equation 1, or say equation 2 basically, okay, in the form of the delta theta. We have seen that E is equal to A del theta plus B del theta square. Okay. So, if I recall that from equation 2, I can say that E is equal to A delta theta plus B delta theta square. We have also seen that the value of B is very less from equation 3. Okay, we have seen that B is 1/10 or 100, or it's just fraction of say microvolt per degree Celsius square. Okay, it can be actually neglected if you compare it with the A value. Okay, so the A value dominates in the equation, and the EMF E can be written as simply A delta theta by ignoring the second term, which is very small, or B delta theta square. Okay. So, this is my fourth equation. Now, this is the EMF, okay, approximate EMF, and this EMF is fed to the permanent magnet moving coil, say millivolt meters, which give a deflection proportional to the EMF E. Okay, and that's how the deflection is directly proportional to the EMF that is generated by this thermocouple arrangement. Okay, so the deflection is directly proportional to the EMF, or say theta is equal to another constant I am calling, say K2 into E. Okay, so one constant we have seen is this K1 from equation 3. Delta theta was equal to K1 I square R. Okay. So, this was the equation 3. Okay. E equal to A delta theta is say we are calling it equation 4. Alright. Now, we have seen that theta is directly proportional to E, or theta is equal to, say I am introducing another constant K2. So, theta is equal to K2 into E value. Okay. Say I am calling this equation 5. Alright. So, equation 4 was E is equal to, or approximately equal to, A into delta theta. Okay. And then I am calling another constant K2, which is theta is equal to K2 into E. Okay. Since we have already approximated from equation 4, this E value was approximately equal to A delta theta, I can say that this deflection is equal to K2 into A into del theta. Okay. Do not get confused between this theta and this del theta. This was the temperature difference, and this is the our deflection. Okay. So, now putting the value of this del theta, okay, from previous equations, I can write that theta is equal to K1 K2 into this alpha value, okay, or say this A value, A into I square R. Okay. Theta is equal to K1 K2 A into I square R. This value was del theta we have already calculated. Okay. Del theta we have already calculated from equation 3 as K1 I square R. Okay. Now, putting this value in this, I have theta equal to K1 K2 A I square R. Fine. So, this is equation 6. Okay. Now, all these terms together, K1, say I am calling this, say K1, K2 R into, say A, all these terms are constants. Okay. So, K1 was one of the constant that we have seen in the equation 3. Okay. This we have seen. Alright. Then A was the constant that we have seen in the Seebeck equation. Okay. Similarly, this R and this A, all are constant. All together this I am calling this as a constant K3. Okay. Now theta is equal to K3 I square, where K3 is itself a constant, or the deflection is directly proportional to I square rather than being proportional to I. Okay. So the instrument shows a square law response. Okay. Theta is, or I am calling this equation 7, theta is directly proportional to I square, or theta is equal to K3 I square, or this is again a kind of square law instrument. Okay. Now the thermoelectric instruments consist of two different major parts. One is the thermoelectric element itself, and second is the indicating instrument. Okay. So let's try to understand this in more detail with a little bit on its construction. Okay. The combination of the heater element and the thermocouple acting as a energy converter is known as the thermo element. So as the name suggests, we have two different parts in this thermo element. One is the heater element and second is the thermocouple itself. Okay. So a thermo element together with a permanent magnet moving coil instrument, which is basically the indicating instrument here. We have seen that two different important things, thermoelectric element and the indicating instrument. So I am calling this permanent magnet moving coil as the indicating instrument in this case. Okay, this indicating instrument. All right. So a thermo element together with this indicating instrument constitute a thermocouple instrument, which is say thermocouple ammeter or say thermocouple voltmeter. Okay. Let's try to understand this thermoelectric instrument in more detail. Okay. So the electric energy is converted to thermal energy in the heater element. Okay. Most of the heat energy is basically dissipated away and a portion of it is transferred to the hot junction in the thermocouple. Okay. Now the heat energy transferred to the hot junction is now converted back to the electrical energy by the Seebeck effect. Okay. The output of the thermocouple is connected to a permanent magnet moving coil instrument, which is acting as a indicating instrument. Okay. A portion of the electrical energy in the thermocouple circuit is converted to mechanical energy in deflecting the pointer and is stored as potential energy in the springs of the instrument. Okay. The overall efficiency of the system is not very high. Okay, and it is of the order of say few hundredth of a percent under most favorable circumstances. Okay. The power consumption of the instrument is very high. Okay. And a sensitive DC instrument has to be used as a indicating element in place of any other AC instrument, although the current is directly proportional to, or the deflection is basically directly proportional to I square. Then also we have to prefer a DC instrument. Okay. So there are four different type of thermo element, and by this different construction only these thermocouple instruments vary in their construction. Okay. The first kind of thermo elements is the contact type, second is the non-contact type. Then for better accuracy, we also utilize other configurations like vacuum type of thermo element and the bridge type of instrument. Okay. Let us see all these different type of thermo elements in little brief. Okay. So that we understand how these instruments work and what is the advantages of using different configuration of these thermo elements and not only one kind of thermo element is there. Okay. So let's first try to understand the contact type thermo element. Okay. As the name suggests, there is certain kind of contact here. Okay. So a separate heater wire is used in this contact type thermo element. Okay. Now one junction, basically the hot junction itself of the thermocouple is kept in the contact with the heater wire. So as you can see in the figure also, you have this heater element and this is the thermocouple, and along with this you have a resistance and this automated temperature compensation circuit. Okay, and all together this is connected to a DC measurement de-Arsenal type of galvanometer. Okay. So one junction of the thermocouple, as you can see here, is connected to the heater itself. Basically this is, of course, as the name suggests, this is measuring the heat flowing through this. So basically the hot junction is mostly kept in contact with the heater. Okay. So this is basically the idea of the contact type thermometer. in the non-contact type thermometer, as the name suggests, there is no electric contact between the heating element and the thermocouple. Okay. So the two part, basically the heating element and the thermocouple, are separated by certain kind of electrical insulation between them. Okay. And the heat is conducted from the heater to the junction across this particular insulation. Okay. So this makes the instrument sluggish and less sensitive than the contact type of instrument. Okay. The separation between the heater and the thermocouple becomes essential for measurement of current in the circuit operated at potential above, say, ground potential. Okay. Then we have the vacuum thermo element. Okay. So this is very much required when you have very low range of the temperature difference that has to be measured. Okay. So for very low range thermocouple instrument, the power absorption also is very low. Okay. In some cases, a power of as small as, say, 2 milliwatt is used in the heater element. Okay. Now, in order to attain a temperature rise of the order of, say, 80 degrees Celsius to 100 degrees Celsius, it is necessary to develop the required output of the thermocouple instrument of the order of, say, 5 millivolt on a open circuit. Okay. So what we have to do is we have to increase the efficiency and sensitivity of the thermo element, and this is done by enclosing the heater as well as the thermocouple assembly inside a glass tube, which is basically is sealed together, and then there is kind of vacuum created in the glass tube. Okay. The efficiency is increased because there is no cooling of the heater due to convection air currents, and of course the complete heat is getting transferred to the thermocouple. Okay. In the bridge type thermometer, there is no heater at all. Okay. So no heating element is used. Instead, the current that has to be measured is passed directly through the thermocouple and raises the temperature directly proportional to I square R. So you do not have a heater, as you can see this arrangement. Okay. You do not have a separate heater, but what you are doing is you are directly passing the current through the hot junction of this thermocouple. Okay. And this rise in the temperature is directly proportional to the I square R value, as we have seen in the heater case. Okay. The cold junctions are at the pin that are embedded in certain kind of insulators like bakelite based plate, and hot junctions are midway between the pins. Okay. Not at the pins, but in the midway between the pins. Okay. As you can also see from the figure. Okay. The thermocouples are oriented as shown over here, so that the resultant thermal EMFs give rise to the DC difference of the potential between the junctions A and B. As you can see, there is a dearsenable kind of galvanometer attached over here. Okay. So no AC current can flow through this instrument, as the bridge is balanced by keeping the equal the resistance in the all these 4 different arms. Okay. This constructions give a greater output than is given by a single thermocouple, even used in the vacuum, and is much more robust in withstanding the mechanical shocks and the overloads, because the bridge is in the balanced state and you are not using a separate heater here. Okay. So bridge type element are made with AC ratings from 100 milliamp to 1 amp, which is not very high, although range looks very high, but some of the arrangement can even withstand current rating till, say, 20 amp. Okay. The voltage available may be as small as 25 millivolt, which is of course higher than what we have seen. Okay. So the advantage of this thermocouple instruments are like they can be used over wide temperature range, as well as the current range is also wide for this kind of instrument. Okay. The construction is simple of all the thermocouple instrument. Okay. And they have rugged kind of construction, and that's why they are very much favorable in the industry. Okay. They have fast response time, and they are basically a self-powered device. Okay. They are suitable for rough ambient. Okay. and they are not affected by stray magnetic field, and they are also free from frequency errors. That's why we have seen that it can be used even at the frequency above than 50 megahertz. Okay, then there are several disadvantages also. Even in the toughest configuration, we have seen that we can achieve to maximum to 25 millivolt, but in general we can achieve say 5 millivolt to 10 millivolt. Okay, so the output voltages are very low. Okay, accuracy is also not very high. Similarly, the sensitivity is also not very high in case of thermocouple instrument. Okay, and the output is very non-linear. Okay, we have already seen the output is in such a way that it has non-linear characteristic. Okay, and they require cold junction compensation most of the time. Okay, so applications based on their advantages are numerous, like it has application in industry, like in pharma industry, in petrochemical industries and so on. Okay, they are very much useful in the process industries, and they are integral part of electrical and electronic instruments. Okay, and of course useful in the aerospace and automotive kind of applications. Okay, so that's all about the thermocouple based instrument. In the next class, we will keep our discussion alive and we'll talk about new kind of instrument, which is the induction kind of instrument, and we'll see that the instrument is basically useful for the measurement of AC signals. Okay, we'll see different flux equations, and based on that we'll derive the torque equation of the induction type of instrument in our next lecture. Thank you.